Hello, everybody.
Hey, Professor.
Hello. And is my screen showing?
Yeah.
Great. Perfect. Okay, so it's 5 o'clock. It's concrete time. Does anybody have some questions that they would like to ask me before we continue on with our lecture?
Professor, I had a question when we talked about homework 6 earlier.
Uh-huh.
When the load is unfactored, that's what you refer to as a service load?
Yes, it is. Uh-huh.
Okay.
Yeah.
And in the field, does that get calculated by the engineer, or can you kind of explain a little bit of how that process works?
Sure, of course. So throughout the history of structural engineering, there's really been two main camps, philosophies on design. One is it goes by several terms, but it's allowable stress design or service load design. And that's always been that the engineer, the structural engineer, always tries to predict what the loads are as accurately as possible. And then we use those loads, but we design whatever it is we're designing to some allowable stress that is much, much lower than the actual stress to cause failure or even yielding. So that's allowable stress design. All the load factors are 1. So 1 times live load, 1 times dead load. That's allowable stress design. That's also what's kind of known as service loads. So service load is really just kind of another way of saying these are the loads I think really will be on the building, as opposed to, and this has a bunch of different terms as well, but as opposed to LRFD or load and resistance factor design or strength design or ultimate design, all of those are basically what concrete has been doing since the 70s. All of those are taking the loads, factoring them up based on how unpredictable they may be, and then comparing them to some close to nominal capacity or slightly reduced capacity, but really based on the load it would take to fail whatever it is you're designing. So concrete, as I said, a long, long time ago, went to factored load design, ultimate strength design, factored load design. And that's what we're doing for flexural capacity, shear capacity. We're in columns now, so axial capacity. But it doesn't make a whole lot of sense to try to predict what your deflections are based on some ultimate load that is just about to fail the beam. That's not what interests you. So even in the world of concrete, we still use service loads to check serviceability issues. I want to know how badly is the beam going to crack under real loads, not under some fictitious 20 elephants in the room load that would theoretically fail the system.
Okay, yeah, that makes sense. Thank you for that.
Okay, yeah, no problem. Any other questions, or anybody want me to elaborate on what I just said? Okay. Okay. Well, if there are no further questions for me at this time, let's continue our lecture on column design. And what's on the screen right now is where we left off last time. And the important thing here is that the code has in chapter 25 this idea that you can have your tie spacing to the least of 16 times the longitudinal bar diameter, 48 times the diameter of a tie bar, or the smallest dimension of the member. So for a 24-inch by 24-inch column with number 8 main bar and number 4 ties, which is very common, then the least of all those would be 16 inches on center. You could have number 4 ties at 16 inches on center, according to the code, everywhere else in the country except for California. California, this is all preempted by the seismic section that we're going to get to in a second. Okay, so does that make sense to everybody? There's like a whole set of requirements that everybody has to follow, and then there's a subset of requirements that only those in seismic country have to follow, and they're much, much more restrictive than what everybody else does. Just as a personal story, I'm used to doing columns. We design and fabricate columns here in California. We've done many, many, many buildings with columns here. And the rules have changed over the years. They've gotten steadily more restrictive. But even 15 years ago, when we were quite a bit more relaxed, we were still putting in our columns, the minimum was a number 4 tie at 6 inches on center. And we thought that was, you know, that's basically to the letter of the code as lenient as you can get. We would never do anything less than a number 4 at 6 inches on center. And then our company acquired another precaster in Minneapolis. So a few of us took a trip out to Minneapolis and met the chief engineer and those guys out there and kind of talked shop about how you do this, how you do that. And we walked around the plant and we saw in one of their column beds, a column, a 24 by 24 inch column, just like we would do to support 4 or 5 floors, a parking deck, just like we would do. And they had number 3s at 18 inches on center. And we're going, holy cow, what are you going to put the rest of the steel in there? And they just looked at us like, what are you talking about? So just an anecdotal story there, but what we do in California and what everybody else does is very dramatically different. Okay, so any questions before we push forward?
So for the homework and for like the test, do we go with the California standards, or do we just go with what everyone else does?
I will be very specific. If something like, I mean, it's a great question, but if something like that comes up, I will be very specific. But it won't likely come up in a homework or even a test situation, because all of this stuff is very prescriptive and it takes a long time to go through and really design out a column with all these prescriptions. Some of this is going to be reference material for you so that you can pull back on this later on and say, what did he talk about? You know, if you find yourself with a column design, I'm laying out as a quick reference for you all these section numbers, where to find this, what are the rules, but not all of this is going to be subject to homework or even the exam. It's the actual column mechanics that are more important for homework and exams. Like when we calculate the actual axial capacity of the column, that's going to be more important. But a lot of this is kind of background information. So I wouldn't worry too much about it. And if there is something that needs to be distinguished, I will be sure to tell you which to follow.
Got it. Thank you.
Okay, so moving forward, let's see, where's my little thing here? We are recording. And just earlier today, I put the last lecture up on YouTube, so you can visit that if you like. Okay, so the maximum spacing, ACI 318.25.7.2, item B, really only applies outside of seismic regions of moderate to high risk. Basically what I just said. Within regions of moderate to high risk, ACI 318, section 18.7. See, now here's what I was trying to say. Chapter 25 is for everybody. Chapter 18 is only for those in moderate to high seismic risk. ACI 318, section 18.7 for moment frame columns and ACI 318 section 18.14 for gravity frame columns will greatly reduce the maximum allowed spacing for transverse reinforcement in your ties. This will be discussed in more detail below. Okay, so tie requirements, tie configurations. Here are some various different tie configurations that you might see. These are all rectangular columns. These are all what we call tied hoops. This is not the spiral reinforcement. This is just tied hoops. But there's a whole bunch of rules about how many legs do you need and how far apart these can be and so on and so forth. So these are just 9 different illustratively different ways to tie really the same shape column. ACI 318.25.7.2 specifies the configuration requirements for ties. First rule A, every corner and alternate longitudinal bar shall have a lateral support provided by the corner of a tie with an included angle not more than 135 degrees. Okay, so what this is basically saying is that you don't have to tie every single longitudinal bar. Like this one has every single longitudinal bar tied, but you don't always have to do that. See this one here, you can skip one, but every other longitudinal bar does have to be tied. No unsupported bar shall be farther than 6 inches clear on each side along the tie from a laterally supported bar. So this here would be okay unless this gets to be more than 6 inches. So whoa, that got really busy. But this is how it works. So like this guy here, I could not have a tie here if this space is less than 6 inches. Same here, I could not have a tie there if this space is less than 6 inches. If that space is more than 6 inches, then we have to do this. We have to put a tie in the middle. So that's why this says 6 inches, greater than 6 inches, I have a tie. Same on the vertical here. Over here, if this was more than 6 inches, I gotta have a tie. And I can use a diamond instead of 2 cross ties if I choose. This guy is okay because every other bar is supported as long as these spaces are not greater than 6 inches. Ties can be provided as hoops or cross ties. See this little guy right here? That's a cross tie. Let me try to hand draw it in so you can see it a little bit better. A cross tie is shaped like this, whereas a hoop would be all the way around with 135-degree ears on it, like so. So you can use either or as long as you follow these rules about which bars need to be tied up. ACI 25.3.5, item E, prescribes that cross ties be alternated end for end. So if you have the 135 here and a 90-degree here, like I've got drawn right here, then as you're building this cage, you have to flip-flop them so that this hook is on alternate ends. Any questions so far? Okay, so for spirals, ACI 318, section 25.7.3.2, the minimum spiral bar or wire diameter is 3/8 of an inch or a number 3 bar. Maximum spacing. The spiral clear spacing is prescribed by ACI 318 25.7.3.1 in accordance A and B. A, it has to be at least the greater of 1 inch or 4/3 of the diameter of the aggregate. The aggregates have to get in and out through the cage. Okay, I had a question about cross ties. Let's back up just a second here. That got awfully, okay, right there. Okay, so if you're only tying 2 bars across like this, you would use a cross tie. But if you have to tie 4 bars, you could use 2 cross ties, or you could use 1 hoop. Okay, yeah, and then the ties, you don't really detail the ties. You just kind of draw them where they need to go, and then the rebar supplier will actually draw up the actual dimensions of these. But as a designer, I would specify where my main steel goes so that I have the proper spacing. And like over here, if I didn't tell them where to put these 2 bars, this spacing might get too big. So as the engineer, I would specify where the main steel goes, and then the ties just kind of follow that. Okay, and spiral reinforcing cannot be spaced greater than 3 inches on center. And that's to get that confining effect like we saw in the photos last time. So here's my round column with a spiral reinforcement. And here's the definitions. D sub C is out to out of the spiral. H is out to out of the column. And dB is the diameter of the tie or spiral. So the volumetric spiral reinforcing ratio dictated by ACI section 25733 has to be greater than 0.45 AG over ACH minus 1 times F prime C FYT, where AG is the gross area of the column, ACH is the cross-sectional area of the column measured outside edges of the transverse reinforcement. So it's the area inside this outside hoop. FYT is the yield stress of the transverse reinforcement, and rho sub S is equal to, so this rho sub S has to be greater than this, but rho sub S is actually equal to this. So you calculate this and compare it to this, where AST is the cross-sectional area of the spiral wire or bar, and D sub B is the diameter of the spiral bar or wire. Protection of reinforcement. Similar to beams and slabs, look to ACI 318 section 20.6.131 for coverage requirements. For columns exposed to earth or weather, ties have to have 1.5 inches cover. Longitudinal steel has to have 2 inches of cover. For columns not exposed to earth or weather, ties have to have 1.5 inches cover. Longitudinal steel has to have at least 1.5 inches of cover. Not a huge difference. Okay, so special requirements for columns in seismic regions. Columns that are part of the lateral force resisting system, the LFRS, primarily columns that are part of the special moment resisting frames, must be designed per the prescriptive requirements of ACI 318, section 18.7. Columns designed to resist lateral loads as required by section 18.7 are beyond the scope of this course. That's like a whole nother, oh man, I could spend 3 or 4 weeks just talking about moment frame design. So that's kind of outside of the scope of this. However, columns not designed to resist lateral loads from seismic, otherwise known as gravity frame columns, still have special detailing requirements when built in areas of seismic risk. According to ACI 318, 1814 gives prescribed requirements for columns not designed as part of the seismic force resisting system. ACI 318.18.431 divides columns into 2 broad categories based on induced moments and shears when deformed by the design displacement delta U. Delta U is found from your ASCE 7 chapter 12 provisions. Just in case I've lost anybody, just in case, let me make a little diagram here. Just make a real simple Okay. And there. And we'll do that. And we'll do that. Okay, so here's a real simplistic little diagram. And can I assume, guys, that you've all been in that concrete parking garage at Cal Poly, or at least have driven by it or kind of familiar what it looks like? Is that a fair assumption?
Yeah.
Yes.
Okay, great, great, great. So inside of that building, you have some concrete columns are very large, very substantial, and they have these fairly large concrete beams framing from column to column. On that building, though, it's actually many frames. It's like, I don't know, 5 or 6 bays of this. But in essence, some columns are really stiff, really big, and they have these big cast in place beams cast in between them. Those are the moment frames. So when, let me draw. Okay, so I'm saying this is the ground, okay? So when there's an earthquake, you have all this mass lumped at every floor. And that mass wants to dance around left to right, right? Just like any earthquake. And the only thing that's really holding that building up are these moment frames, like I've drawn here in these big heavy beams, big heavy columns. It's the moment frame that keeps the building from flopping over, basically. And that's what I say when I say up here that columns to resist lateral loads as required are beyond the scope of this class. That's these columns. These columns are part of the moment frame, and they're very, very strong. They're very large. You can't miss them if you drive through the building. But you also have a bunch of these columns over here. And these columns do not have very large beams framing into them. They have smaller beams supporting the floors, but they don't have these really big beams. And these smaller columns are not designed to keep the building from falling over in an earthquake. That's not what they're designed to do. This is my earthquake motion. They're only designed to carry the vertical load from all of you parking on there and all the concrete. So some columns are only designed to carry the vertical load, and some columns are designed to carry this very large seismic induced moments and shears. Okay, so does that make sense so far?
Yes.
Okay, and Ashley, don't mean to call you out, but so far so good?
Professor, can you repeat that last part?
Yes, I think.
I don't, like when you were talking about the thinner column is not designed to take the seismic load, right?
Right. Yes. Okay, so let me try to freehand this a little bit. Say like the earthquake is trying to shove the whole building that way. So these columns bend. Okay, something like that. But these columns and beams get twisted and contorted and they're bending, and it's the strength of these beams in bending and columns that is actually holding up the building laterally, from flopping over. These columns, they bend as well, but only because the whole building is drifting. Their stiffness against the lateral load doesn't matter. They're not holding the building up from side sway. The moment frames are keeping the building from falling over. These guys just go along for the ride. Does that make sense?
Yeah, and you said they're supported more on the base. Is those
Well,
yeah,
they're all fixed to the foundation, but
okay.
these guys are designed so that they can resist large moments as they're being bent around. These are not designed for large moments. They just get bent around. So historically, what has happened, these are the two kinds of columns we have. We have lateral force resisting columns here. Lateral force resisting system. And then you just have these guys are called gravity columns. I cannot write with this mouse, but I think I can squeak out gravity. There you go. Okay, so these are moment frame columns, part of the lateral force resisting system. These are gravity columns, but they're all tied together with this concrete slab. When you drive into that parking garage, everything is tied together with the floor. The floor is a big concrete slab. So whatever the frame is doing, these gravity columns have to do the same thing in terms of lateral displacement. So what I'm trying to say is section 18.7 covers the design of the lateral force resisting system elements. And section 18.14 covers how we have to detail these columns. Even though they're not resisting earthquake loads, they're still being shoved around. And if you don't make them ductile, then you could have explosive failures down here at the bottom. So even though this column is not resisting earthquake loads, it gets pushed over and it could lose its vertical load carrying capacity, right? So that would be really bad. That's exactly what happened in that photo that I showed you last time of the rectangular column where all the concrete was just completely destroyed. That wasn't a moment frame column. It was just a gravity column, but it got beat around and pushed around so much that it basically destroyed the bottom portion of the column. So if everybody's okay, if everybody's up to speed, that's what we're talking about. We're talking about new code provisions that require us to detail our columns that are not part of the lateral force resisting system just to have enough toughness to be pushed around by an earthquake and not explode.
And Professor, are those moment frames are there multiple columns up around the structure? Like
Yes,
say the Cal Poly one?
yes, yes. So what,
Okay.
yeah. Do, 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 do. Do, 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 do. If this is a typical building, I mean really typical building, then what you'll see is that maybe you have a line of moment frames here, 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 there, and then maybe for the other direction, here, here, something like that. So each one of these boxes actually represents maybe 4 or 5 columns with beams in between. So this would be one moment frame, this would be another moment frame, this would be a longitudinal moment frame. Does that help?
Yeah, that puts it into perspective. Thank you.
Okay, yeah, no problem. So let me draw these little guys right here. So that's a moment frame column. And like I said, I'm going to try to draw all of them, but maybe one frame has 4 columns. So these 4 columns in this moment frame have to be designed by 18.7. But we're also going to have columns out here in the building that are picking up all this gravity load, but they're not part of any kind of a moment frame. Those are the 18.14 columns that need to be detailed so that when the whole building starts drifting back and forth, they don't explode. Okay. Ashley, are you up to speed, or do you still need more help? Yes, great, 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 great. Ashley's happy. Okay, let's go forward. Okay. So we have two broad categories of these columns that are not part of the seismic force resisting system. Of our gravity columns, we have two broad categories. We have columns whose design strengths VMN and VVN are not exceeded when the moments and shears are induced by the drift. So the earthquake hits and the columns are still perfectly fine. This never happens. So just forget about that, A, at least not in California. B, columns whose design strength VMN and VVN are exceeded when the moments and shears are induced by the drift, or in cases where delta U is either unchecked or otherwise unknown. This is where we live, right here. You push a column over 1.5 feet, you're gonna exceed its shear strength. That's just what happens. But that's okay. That doesn't mean it's gonna fail. It just means that you have to put more steel in there for more ductility so that it can bend around and not fail. In most cases, in real world examples, case A is very difficult to justify. Generally, most columns will fall into case B requirements. Additional detailing requirements. Columns whom design strength VMN and VVN are not exceeded when moments and shears are induced by the drift delta U per ACI 318.18.14.32b. Columns must be satisfied ACI 318.18.741, 752, 1876. I know this gets a little tedious. Pretty much this is going to be reference material because this does get a bit tedious. But I'm briefly hitting the points of what you have to do to make these columns work in California. So 18741 says the area of longitudinal steel must be between 1 and 6%. Remember, everybody else can go to 8%. We have to hold it to 6%. 18752, transverse steel must be in accordance with A through F. Transverse steel shall be made of single or overlapping spirals, circular hoops, or rectilinear hoops with or without cross ties. Bends and rectilinear hoops and cross ties shall engage peripheral longitudinal reinforcing bars. Cross ties of the same or smaller bar size as the hoop shall be permitted. Where the rectilinear hoops or cross ties are used, they shall provide lateral support to longitudinal reinforcement in accordance to basically the 9 columns I showed you just 10 minutes ago. That's what all this is. You have to follow the reinforcing that I showed you in those 9 illustrations. Reinforcement shall be arranged such that the spacing h of x of longitudinal bars shall not exceed 14 inches. H of x is measured center to center of longitudinal bars. And where PU is greater than 0.3 AG F prime C, or F prime C is greater than 10,000 PSI, H of x shall not exceed 8 inches. 1876, shear strength. These provisions specify that the shear demand VU will be found by calculating MPR at each end of the column and dividing by the story height, which is beyond the scope of this course. Additionally, the maximum spacing of transverse steel shall not exceed S naught equal to the lesser of 6 dB or 6 inches, where dB is the least diameter of the longitudinal steel. So here's what I was talking about. Where everybody else can design to, 16 dB, here we are 6 dB, much, much tighter steel spacing. Per ACI 18.14.3.2, C, columns with PU greater than 0.35 P naught must meet all of the above plus the following. So if you have a fairly substantial axial load, you got to do all of this plus. Basically states that any concrete more than 4 inches outside the transverse steel required also needs transverse steel. Where did 0.35 come from? Some think tank somewhere. It came from committee work. It came from, there actually is a number for it. We haven't talked about the column interaction equation yet, but it comes from that. So when we get to there, remind me and I'll tell you what the 0.35 was supposed to represent. Transverse steel must be at least half of what is required by ACI 318-18754. And transverse steel required area, where ASH is the area of all legs of hoops or cross ties spaced at S transverse to BC, where S is the spacing of the sets of hoops or cross ties, and BC is the width of the column perpendicular to the direction of interest. Okay, so I'm glad I finally came up with an illustration here. So when we evaluate these, and this is really complex. Again, this is really, a lot of this is just for your reference because this is getting kind of complex. But what we have to do is if the earthquake is in this direction, then we have to size these legs of steel and we have to size the spacing of the steel such that we provide this total volume of steel over this BC, which is this width. And it can amount to a substantial amount of steel for a column that's not even designed to resist earthquakes. The calculation of the actual required area steel is outside the scope of this class. It is actually the same as designing a moment frame column, but see ACI 318 table 18754 for required area of steel. Columns whose design strengths Vmn or Vn are exceeded when moments and shears are induced by drift delta U or delta U is unknown. All of the requirements of above, except that ACI 318-18754 must be provided in full, not half. I said a moment ago that the steel that you would get from following the moment frame requirements, you can get away with only using half of it. Well, not if your column strengths are exceeded, which again, this is almost all the time. So basically every concrete column in California pretty much has to be detailed like it's a moment frame column. Additionally, ACI 1875 and 1876 must be complied with. ACI 18753 specifies the maximum spacing S naught in the N regions L naught as 1/4 of the minimum column dimension, 6 times the diameter of the smallest longitudinal bar. This equation here, and see this little h of x? H of x is the distance from bar to bar. And what I read to you a moment ago said that if the column is under 0.35 P naught, then this can be as much as 14 inches. If the column load is more than 0.35 P naught, this spacing cannot be more than 8 inches, which really is a lot of steel, but not greater than 6 inches nor less than 4 inches. And this end region where you have to put all this steel is the depth of the column at the joint face or the section where the flexural yielding is likely to occur, or 1/6 of the clear span of the column, or 18 inches. So in summary, columns will be required to have heavy transverse steel at a maximum spacing of S naught for a distance of L naught from each end of the column within a story, and a reduced spacing of 6 dB or 6 inches for the middle portion of the column. In most cases, many more longitudinal bars will be required, at a maximum spacing of 14 or 8 inches, depending on the magnitude of the axial loading. The goal of all this regulation is to prevent that, right? That was a hospital, as we talked about, the San Fernando earthquake, and this hospital almost completely collapsed, which, as you can imagine, a hospital completely collapsing is pretty much the worst structural engineering failure pretty much you can think of. And it got really close. So this had no confinement. So we're going to start requiring, and I got this neat little graphic here. This is what you're seeing here. This is how we used to do it, where you just have 4 corner bars and these little spindly ties at some pretty exaggerated spacing. Let me get to that question in a second. Okay, this is how we used to do it. And that's what this was. See that little tie right there? That's that little guy right there. And then there's another one way up here. Now we are doing this. Everything that I just explained in the last 20 minutes is this. So you have very heavy steel at the top and the bottom of the column, and you still have fairly heavy steel in the middle of the column. And instead of these 90-degree bends, you have 135-degree bends with intermediate ties and intermediate longitudinal steel to really make what this was very, very brittle to make something very, very ductile. And that is the definition of ductile. See these guys right here? This is unbelievable. This was a moment frame. It was designed to resist lateral loads in the left and right direction. But what happened on this particular building, this was Northridge, and columns in the interior of the building exploded. They had a short column effect and they exploded, and it basically imploded the building. The whole building kind of sucked in on itself. So it pulled this whole frame over out of plane. Well, so this looks like a dismal failure, but really it is quite a remarkable, because these columns were detailed to be so ductile that they bent over like 90 degrees from the ground, and they're still concrete. It's still a viable concrete column. It's just got bent in the wrong direction. Here's some close-up of it. Yeah, there's a lot of yielding, there's a lot of cracking, but this is a very ductile failure compared to this. See the difference? So that is a very ductile failure. And so really these were moment frames, so they had a ton of steel in there like we've been talking about. This is what they're making us do for gravity columns as well, so that they can bend over super far and not explode and still be able to carry the building. Okay, let's see. The first question was, why can epsilon t be less than 0.004 for columns? It has to be, because in many, many cases, the load on a column is compression. So everything in the column is in compression. You can't require that epsilon sub t be more than 0.004 in tension when everything is in compression. So that doesn't make any sense. You have to give it the full spectrum for something that's designed to carry compression. It just means that it's going to have a much lower phi factor. Phi is going to be 0.65 or 0.7 instead of 0.9 for beams. So that's what you give up for that. Ductile means to be able to bend under lateral load. In the strictest sense of the word, ductile means that it can bend and bend and bend some more, and it doesn't fracture, it doesn't break. Okay, so classic example. Everybody has been bored at some point in their lives. I know, not right now, but at some point, everybody has been bored. And when you get bored, what do? You pick up a paper clip and you start bending it around and making it into a triangle and then using it to scratch your ear or something like that. When you bend a paper clip, how many times can you bend that thing around into a pretzel until it finally breaks? Well, it will finally break, but you can really kind of twist that thing around your finger and it doesn't fracture. Paper clips are very ductile. Try taking a piece of chalk and wrapping that around your finger. Chalk is very brittle. Okay, so that's my definition of brittle versus ductile. Okay, any other questions on, that was the intro to columns. I will be honest with you that what we covered in this lecture, the axial load stuff is essential because that will be in the homeworks, that will be on the tests. All of this tie stuff that we did basically today, this first hour of today, is really more for reference. I don't expect everybody to memorize or master all this stuff. And that's also why I kind of went through it kind of quick, because I could spend 6 hours just on tie spacing. And I don't think anybody would survive that. So any final questions?
Professor, the gravity columns you said are designed similarly now to the moment frame columns,
Yes.
except they're framed with smaller beams like you illustrated earlier. Is that one of the, and they tend to be like a smaller diameter, or?
Well, they are smaller. They don't need to be as large as moment frame columns because moment frame columns need to be a lot stiffer or else your building will just bounce out of control. But the main difference, the huge difference, is when you design moment frame beams and columns, it is the actual seismic lateral loads that you are designing against. So you're going to build a frame in your software packages, ETABS, RISA, RAM, whatever, and you're going to apply to this frame your lateral loading. And that's what you design against. So your moments and your shears come directly from the lateral loading. Gravity columns, you do not design for lateral loads. It's not resisting lateral loads. It's only resisting the loads that are coming from gravity from your structure. So you basically do your whole column design based on no earthquake, based on just what's there all the time, gravity. But then when it comes time to detailing your column, then you got to pull into all these prescriptions about the detailing of the column. How many bars do you use? What's your tie size and spacing? And all of that comes from what we just talked about. But you're not designing to an earthquake. You're just detailing to all these prescriptions. When you do the moment frame, you are designing to resist the lateral loads and following all these prescriptions for your detailing.
And just to recap, the moment frame, is that taking any gravity load or just lateral?
No, they can. They can. They could be designed to take some lateral load. Generally, not too much. Generally, it will be taking its fair share of the building and the floor and the live loads, cars, whatever. But if you, again, thinking of the example of the Cal Poly parking garage, if you go near there, what you'll see is that the gravity only columns are 18 feet on center in the one direction, like east-west, but they're 62 feet apart in the north-south direction. The moment frame columns are like 18 feet apart. So they're much closer space with much bigger beams. So they pick up some gravity, but not nearly as much as the gravity columns. Okay, any other questions before we jump into lecture 11? So what we're going to start talking about today, or let me recap what we talked about last time. Last time we looked at, from a mechanical material point of view, how much load can a column sustain before it just explodes. But that column, we restricted our conversation to columns that are concentrically loaded only, no moments, no eccentricity. And so all the fibers of the column are loaded equally, all at the same time. So the concrete will crush across the entire cross section and the rebar will yield all at the same time. And then what that was P naught, and then we looked at Pn, and then we looked at Pn. Well, that was all, again, just concentrically loaded. Now we're going to take the conversation to the next big level, and that is columns with combined axial load and bending moments. And just for those of you who tuned out because I started talking about all the ties and the spacings and everything, now's the time to come back, because this is the real stuff that we actually use to design with. Okay, so without any further ado, we need to define the plastic centroid of a cross section. A plastic centroid of a cross section, we look at the fully yielded condition of all the elements. So if I have steel here, then that's the yield times the area of steel. At the center of all the concrete is 0.85 F prime C Ag minus AST, and at the centroid of this steel, Fy AS2. And P naught is located at the resultant of C1, C2, C3, which equals the plastic centroid. So in other words, you need to know where the centroid of the column is, so that if your load is not on the centroid, you know what the proper eccentricity of that load is. Eccentricities of load, E, we always use a little e to designate eccentricity, are measured from the application of load to the plastic centroid. Now, most of the examples that we're going to do, the plastic centroid is right smack in the middle of the column, because we're going to be primarily looking at symmetrical columns. But I just want you to be aware that the plastic centroid may not always be at the center of the column. If the cross section is symmetrical, then the plastic centroid lies at the geometric center of the section, which is what I just said. Okay, so effects of combined loading. If I have a column and I have an axial load and I have a moment, right? Then, see, how did I do this? Okay, so case number one, if I have 0 moment, I have pure compression, then the strain in the steel is equal to the strain in the second row of steel, equal to the strain in the third row of steel, equal to the strain in the concrete. Everything is straining together under pure compression. If I have a small moment and I have a large axial load, then you can see that the strain is skewed, so that the center of the resultant of the load has shifted a little bit, so that epsilon S1, epsilon S2, epsilon S3 are all still in compression, but they're less than yielding. Okay, so you see how if the moment went off to one side a little bit, then you have this skewed strain. If I have a medium moment and a large axial load, so now the moment's getting bigger, then I need to start having some tension in my steel to resist that bending moment. So I still have steel and compression on this side, I have steel and tension on this side, and notice that the maximum strain in the concrete is always 003. If I have a large moment and a medium axial load, then epsilon S1 now is going to be equal to the yielding strain. Epsilon 2 and 3 will be less than yielding strain. And so now you have some compression and now you have some tension. And then, let's see, the balance condition occurs when the steel yields just as the concrete crushes. So if you have a condition of loading that is so precisely, finely tuned balanced that epsilon C equals 0.003, just as the steel hits the yield, that's the balance condition. And then lastly, we could have a very large moment, a very small axial load, and the strain in the steel one is much larger than the yield. And what is this starting to look like? What behavior is this starting to feel like?
A beam.
Very good. That's exactly what I was looking at. If the axial load is getting very small and the bending moment is getting very large, then really this is just a vertically oriented beam. And this would be solved using the principles that we learned for beams. So this is the progression. This is going from axial load with 0 eccentricity to a little more, and a lot of eccentricity. And this is how the strains behave. Any questions on this slide? Oh yeah, one other thing. This is the balance condition where the steel has yielded just as the concrete is crushed. Anything less than this is compression controlled, and anything more than this is tension controlled. So this is where those epsilon sub t's come in. I think I can answer that epsilon sub t question now. Epsilon sub t down here for a beam has to be at least 0.004. But as you can see, this condition is not going to be 0.004. This is 0.0207 for yielding. This is less than yielding. And these situations are actually in compression. So you have to have the whole spectrum for epsilon sub t to cover all these cases. In the compression controlled region, phi is going to be 0.65. For balance, phi is still going to be 0.65. And for tension controlled, it's going to progress and ultimately be 0.9. Okay, and I think I just said what I'm about to say. If mu is equal to 0, you have pure compression, compression controlled, phi is equal to 0.65. And what I'm illustrating here, remember A, this is your Whitney stress block. So now I'm showing you what happens to the stresses. The last slide was strain. This slide is showing you the stresses for each one of these conditions. So here, all the steel has yielded in compression, and the Whitney stress block is the width of the whole column. The whole column is in compression. Number 2, add a little bit of moment. A now is smaller than the width of the column, and the stress in the steel is a little bit less as you get towards the outside edge. Phi is still 0.65. A medium moment, now some of your steel is in tension, and your stress block is getting smaller, but you're still at 0.65 until your stress or your strain here gets over 0.004. This will continue to be 0.65. Large moment, balance condition. We still are at phi equal to 0.65, but A keeps getting smaller and the tensile stress keeps getting bigger. And then finally, this is more like a beam where now you have a yielding stress here and you have A is quite small. This is tension controlled, phi is equal to 0.9. Okay, so kind of putting it all together. This is your stress diagram. This is your strain diagram, compression controlled, balanced, and tension controlled. I uploaded this presentation, so you might want to print this out or at least keep this handy. because what we're going to end up doing is for the design of one column, we're going to calc out all 5 of these positions. That's the procedure for designing these columns with combined loading. So as we're calculating out these 5 different positions of, we're going to label them A, B, C, D, and E, it is helpful to kind of keep this in your mind of what it is you're trying to do. And so that's, I would keep these for reference. Balance condition occurs when the tension steel yields simultaneous with the compressive failure. So that's right here where the steel has hit yield at the same time that the concrete hits 003. A balance condition is a result of a unique combination of axial force and bending moment. From the strain diagrams, you can see that in many cases, the stress in the steel Fs is less than the yielding stress Fy in tension or compression. That's going to make it a little more complicated. That hasn't yielded here. This one hasn't yielded. That one hasn't yielded. And here, these haven't yielded. So we're going to have to figure all that out. This can make solving for a specific case of axial load Pu and Mu very cumbersome. What I'm basically trying to say here, for a beam, you guys determined the moment. Mu is equal to 1200 kip feet. Then you designed the beam to handle that moment specifically, and you checked it with phi mn greater than mu. In columns, you can't really do that because there's an infinite combination of axial load and moment. And it makes it very, very cumbersome to try to calculate the exact strain condition for the whatever loading condition you have. So we're not going to do that. We're going to do something simpler after we take a break. So 6:10?
Perfect.
Okay, be back at 6:10. Okay, 610. Everybody back?
Yes.
Okay.
Yes.
Okay. All right, here we go. Columns with combined axial load and bending moments. We need to convert a moment to eccentrically applied load. Okay, so what we're saying is a column that has an axial load and an applied moment is equivalent to a column that just has an applied axial load at some eccentricity E. Actual loading and equivalent loading for a concrete design. Large moment produces a large E, eccentricity. Okay, so as I was saying before, with beams, you only have one variable, the moment. So we could actually design the beam so that the beam's phi mn satisfies is greater than mu. Columns, not so much, because there you have axial loads and moments in varying degrees. There's an infinite combinations. So instead, we use interaction diagrams. And this is what an interaction diagram looks like. And so it's a plot of the capacity, but as the moment goes up, the axial capacity goes down. So the maximum axial capacity that you can get is if you have zero moment, which is right here along this axis. And this is what we calculated last time for P naught. But as you increase the moment, it decreases the axial load capacity. So what we're going to do is calculate several points along this curve and then draw just kind of a simplified segmented version of this curve together. And then to evaluate it, if the load, if you plot the load, like you go up the axial load and you go over the moment, and that load is inside the curve, then it is acceptable. If you plot the load going up and the moment over and you end up outside of the curve, then it is unacceptable. It won't be, the column's not sufficiently strong to carry that load. And then we also have this balance point that we talked about where the steel yields at the same time the concrete crushes. This is the balance point at the moment and the axial load that causes that balance. Okay, so this gives a more complete picture of a column's capacity. Every point on the red interaction curve represents a capacity at failure for a combination of P sub n and M sub n. Each point represents exactly when epsilon sub t is equal to 0.03, where the concrete crushes. Also that 0.35, where did the 0.35 come from? Is roughly this row balance right here. So roughly speaking, this is 35% and this is 65%. And so if your axial load is above this point of balance, that's when you have to start putting in more ties. Okay, so the axial capacity of a column with zero moment is here. That's what we did last lecture. The axial and flexural capacity of a column at the balance condition is here. The flexural capacity of a column with zero axial load is here, otherwise known as a beam. And we can plot this point right here. This is a slope. The slope is axial load over moment, rise over run. So since eccentricity is defined as E is equal to M over P, then 1 over E is equal to the slope of a radial line from the origin to the failure point on the curve. So as you sweep from here to here, as you kind of go around this, this line from the origin to any point on the curve is the inverse of the eccentricity. So as you get to here, this has zero eccentricity, and along this plane here, you have infinite eccentricity. and everywhere in between. Slope of the line represents the eccentricity of the balance condition. Eccentricity equals 0 on the vertical. Eccentricity equals infinity on the horizontal. So basically, to say if you have 0 axial load, then any moment divided by almost nothing is infinity. And the moment capacity is reduced by less axial load. So as you get from the balance condition down, the less axial load actually takes away from your capacity for moment capacity. And conversely, once you get to the balance point, more axial load starts reducing your moment capacity as well. This is the compression controlled region. Oh, I was going to say the other part. Let me go back. Oh, I missed it. Okay, so from balance condition up is the compression control region. From the balance condition down is a tension controlled region. Okay, so any questions on the interaction diagram?
Professor, is the unit for eccentricity length?
Yes, it is. Yeah. So if eccentricity equals moment over axial load, so you have kip feet over kips, so eccentricity is measured in inches or feet. Good question. Any other questions?
Is that length expressed in the column? Like in the previous picture, I think you showed.
Right there.
Okay. So
Yep.
it's from the center to your load?
Yes, yes. But remember when I said the center, if it's symmetrical, then that is the center. But if it's a non-symmetrical column, it's the plastic center. But yes, from the center to the load is the eccentricity.
Okay.
Okay. So now we have design interaction curves. So remember last time we had P naught, and then we multiplied P naught by 0.8 or 0.85 to get the Pn. That's this reduction right here. Let's say we used 0.8. So this would be a 20% reduction from P naught to Pn. And that was the example we did last lecture. But what this is really accomplishing is it's creating a minimum eccentricity. ACI 22421 and table 22421 prescribe that Pn is equal to 0.8 or 80 or 85% of P naught, depending on the use of ties or spirals. So if I draw a line from the origin to this point, the slope of this line represents an eccentricity. This is the new minimum eccentricity. See, so if you had like no moment at all, you still have the same capacity as if you had this much moment all the way over to here. So any design that has less moment than this point here is still designed for this point. So it's basically a minimum eccentricity. But you don't have to think about it. In the old days, we would design the P naught, but we would have to calculate an actual minimum eccentricity and push ourselves away from this axis out in here someplace. The eccentricity created by this reduction on P naught represents the minimum design eccentricity for the column. Slope represents, that's minimum eccentricity. The diagram is still a representation of nominal capacity. So this curve here from Pn to Mn is nominal capacity. For allowable capacity, we must look to table 2122 for the applicable phi factors. And this is what it looks like. So what I've done is this diagram, every point along this diagram was multiplied by phi. For compression controlled, phi is 0.65. So the blue line represents the allowable capacity, phi pn to phi mn, and phi is 0.65 for compression controlled. So this dropped dramatically. See, this dropped 35% due to phi. And you reduce both the flexural and axial capacities together by the same phi, 0.65. So the allowable moment came in 35%, and the allowable axial load came in 35% in the compression controlled region. But down here, where you're in the tension controlled region, and you basically have no axial load all moment, then phi is 0.9. So this only was reduced by 10%. That's how you get this funky shape. It's the difference, the phi factor. And from here, right about here is where you start building from phi equals to 0.65 to phi equals 0.9. And so there's a linear change between phi of 0.65 and phi of 0.9. Notice the kick in the diagram towards pure moment due to the linearly increasing phi factor in the tension-controlled area, as I just described. Okay, so your design interaction curves. What you do is you create this curve. To design a column with combined axial load and bending, we must first construct a design interaction curve. That's the blue, Vpn, Vmn. Then we plot the points of our factored loads, mu in the x direction, pu in the y direction. So I go up and over, and that's my load. If the point falls within the curve, the design is adequate. If not, then the design is not okay. Okay. Any questions before we do our first example?
I'm not sure if you're going to go into this next, but how do you determine if your load falls within like the medium or large load, like, and determine what phi to use? Are we going to get into that?
That's a good question. Not so much, but because. Okay, I can show it here. The no moment is right here. The small moment is here. The medium moment with medium axial load is here. And the large moment with no axial load is here. They're all on this. Remember, this is what we're going to calc here. And then we're going to reduce it by phi to get to here. So this is what we actually calc out is here. So all 5 of those conditions are represented by one red line. One of the points is here, one of the points is here, here, and here. Does that make sense?
Yeah, so once we calc our moment, we use the interaction curve to figure out our phi, or?
No.
Okay.
No. Creating the red diagram, you don't need any load information at all. You just need section properties. So if you have the column and you know the steel and you know the concrete, then you can create the nominal capacity with no knowledge of the demand at all. And then from the nominal capacity, you create the allowable capacity still with no knowledge of the load at all. This is just a function of the column itself. And then you plot your demand in it. And if it's inside, you're okay. And if it's outside, you're not okay. But the load has nothing to do with this shape.
Okay.
Okay?
And we find, so when we find our, like, generating this curve, you said requires no information about the load?
Correct.
Okay.
Because one physical column, you generate one interaction curve for one column that would cover any possible combination of loading. You see, the points you have inside of this curve, you have an infinite number of points. You can go up this far, go over that far, go up this far, go over that far. You could, there's an infinite combination of MU and PU. That's why it's impossible to basically design a column for your loading. But if you design an interaction curve, then you have captured all these infinite number of loading conditions that would be okay. And you've also defined the infinite number of loading conditions that would not be okay. So you build this first, and it's just based on the column, and then you plug in what the actual demand is, and that'll tell you if the column was okay or it's not okay.
So this is our check for capacity for a column, like the method we take?
Yes,
Okay.
yes, Okay, so example 1, here's my column. So again, using the terminology that we use for beams, we are in the analysis mode. Design is quite a bit more complicated with columns. We haven't even begun to talk about design yet. We're just in analysis. So analysis means everything is defined. Does the column work or does the column not work? That's analysis. So this is the column that we want to look at. It's 16 by 16 with our 2 rows of steel, 4 number 9s in each row, 2.5 inches from the face. Given the concrete is 5,000 PSI, it is a tied column. So I didn't draw them in here, but there's hoops. The steel is 60 KSI. The factored axial load is 400 kips. The factored bending moment is 200 kip feet. What is required? Construct a column interaction diagram by finding the phi-pn and phi-mn points for each of the following. And these are different conditions. You have pure compression, 0 tension at the tensile steel, a balance condition, a fully yielded condition where the steel is equal to 0.005, and finally a 0 axial load condition. So these 5 are going to be close enough to draw a sufficiently accurate interaction diagram so that we can be assured that the load is okay or not okay. Is the column safe to carry the design loads? That's what we want to know. Solution. Let's start with point A, pure compression. So pure compression is what we did last lecture, where everything is equally and evenly strained to 0.003. So we calculate P naught. P naught is 0.85 F prime C, area of concrete minus the area of steel, plus the yield of the steel times the area of steel. The area of concrete, 16 by 16, 256 inches squared. Steel is 8 times number 9 is 1 square inch. So that's 8 square inches. So I can just plug and chug 0.85, 5 KSI, 256 minus 8 plus 60 times 8 is 1,534 kips. That's P naught. Pn is 80% of P naught. So I have 0.8 and that equals 1,227 kips. Phi-Pn is 0.65 times Pn. And how do I know that it's 0.8 and 0.65? How do I know those two numbers are right? Right here. Assume it's a tied column, okay? You might have to go back to the last lecture and look through those. Make sure you know where to find this. But if it is a spiral column, these are different. If it's a tied column, 0.8, 0.65. Okay, so make sure you know where to find that. 0.65 times 1227, 798 kips. So this is my nominal capacity with 0 eccentricity. This is my nominal capacity. This is my allowable capacity. And this will come into the chart. Okay. And then phi mn is equal to 0 by definition and observation of symmetry. This is absolutely symmetric. There is no moment capacity in this because everything to the right of the center is balanced by something to the left of the center. Just by symmetry, there is no moment induced into this. So the moment phi min is equal to 0. Point B. Any questions on point A? Okay, point B. Now we're going to look at the condition of zero tension. This is my strain situation. And this right there, see, I've drawn this to line up with this diagram. So this steel has some compressive stress F sub S in it. This row of steel has zero tension, zero stress. And the reason that we picked this, because it's very convenient that I know exactly where C is. Remember, C is the distance from the compression to the point of zero strain or zero stress. So C is defined by the problem to be exactly equal to D, the distance from the compression to the center of the steel. C equals D, which equals 16 minus 2.5, 13.5 inches. Beta 1 is equal to 0.80. I just looked it up in the table this time for 5,000 PSI concrete. And A is beta 1C, 0.8 times 13.5, 10.8 inches. So the force in the concrete is 0.85 F prime C, and area of concrete gross minus the area of steel. So in this case, AG is not the whole column anymore. It's just the area of the width times A, little a. So I have 0.85 F prime C, A times the width minus the steel, but I didn't subtract out all the steel. I only subtracted out the steel that is located in the compression zone, which is half of the steel. So I get 717.4 kips. C sub S is the stress in the compressive steel times the area of the compressive steel. But has the compression steel yielded? That's the question. From similar triangles, which there's your triangles right there, right? So the strain in the concrete over C is equal to the strain in the steel over C minus 2.5 inches. So I solve for epsilon prime S, and I get 13.5 minus 2.5 times 0.003 over 13.5. And that gives me 0.00244, which is greater than the yielding strain. So therefore, the compression steel has yielded. And back to what I was talking about right here, little a is the width of the compression block. The steel over here is not in the compression block, so I don't take that out. I only take out the steel that's located inside of A. And I only add the concrete and compression inside of A. So that's why A was 10.8 inches. That's why my compression zone is 10.8 times 16. And the steel in the compression zone was 4 square inches. Is everybody clear about that part?
Professor, the yielding strain, is that the 0.00207?
Yes, it is.
Okay.
Yes. Yes, which can be found by taking the yield divided by 29,000 KSI. So 60 over 29,000 is 0.00207. Okay, so if the compression steel has indeed yielded, then the force in the compression steel is equal to 60 KSI times 4 square inches, 240 kips. If I sum the forces in the vertical direction and I solve for Pn, Pn is it's actually the externally applied load, but it's the externally applied load under this exact condition. So this Pn is not Pu. It's not the load that you're trying to solve for. It is just a load that causes this exact condition. And we need to solve for it. So I sum my forces minus Pn, because it's going down, plus C sub C and C sub S going up has to equal 0. So therefore, Pn is equal to 717.4 plus 240 is 957.4 kips. So to say it in reverse, it takes 957.4 kips to create this condition. To find m sub n, we sum the moments about the right side edge, summing moments equal to 0. So I'm actually summing them about this point right here. So I have Pn times h over 2, because Pn is always down the centroid. So the distance from the centroid to the right-hand edge is h over 2. C sub c is a over 2, and c sub s times d prime. Summing all these forces, 957.4 times 8 minus 717.4 times 10.8 over 2, that's a over 2, minus 240 times 2.5 is d prime. Pn, I made Pn positive because it's turning it counterclockwise, and the other two are turning it in the opposite direction. So this term is positive, these terms are negative. And I get 3185 kip feet. That is actually, I missed the decimal point. I think that's kip inches. Definitely missed something there. 3185. Yep. Okay. Sorry about that, guys. This is kip inch, which is equal to 265.4 kip feet. Since epsilon sub t is less than epsilon y, epsilon sub t is actually equal to 0 because we defined this to be equal to 0, then phi is 0.65. So phi Pn, 0.65 Pn is 0.65 times 957.4, 622 kips. Phi Mn is 0.65 times Mn, 0.65 times 265.4 is 173 kip feet. So that's point B. All of this determined these 2 points of point B. Point C is the balance condition. By definition, the tensile steel has yielded from similar triangles. I have a picture that's going to pop up here, right there. There it is. Okay, so the balance condition means that the strain in the tension steel is exactly 00207, yielding, and the strain in the compression of the concrete is 003. By definition, this is the balance condition. So from this, we can solve for little c by using similar triangles. C is equal to 13.5, which was D, 003 over 003 plus 00207. C is 7.99 inches. A is beta 1C, so 0.8 times 799, 6.39 inches. That gives me little a. My compression in the concrete, 0.85 F prime C, AG minus AST. Same deal, only now A is 6.39 inches. So the area of concrete is 6.39 times the width of 16 minus all the steel that's inside of A, which is the same 4 square inches. So my concrete compression now is 417.5 kips. My compression steel, did it yield? Well, this is from the same similar triangles that we did before. 799 minus 2.5 times 003 over 799 is 00206, which is less than the yielding strain. So the stress in the compression steel is 00206 times 29,000 KSI. This is Hooke's law, remember? Strain times modulus equals stress, and that equals 59.78 KSI. So the compression force in the steel is 59.78 times 4 square inches, or 239.1 kips. The tension, now this time I have a tensile force. The last point we defined the tensile to equal 0. Now it's not equal to 0. And in fact, because we defined it to be yielding, we can use the yield stress. So that's 60 KSI times 4 square inches gives me 240 kips. Sum the forces in the vertical direction to solve for Pn. Sum the forces equal to 0 minus Pn plus C sub C plus C sub S minus T all equals 0. So Pn equals 417.5 plus 239.1 minus 240 equals 416.6 kips. Define M sub n, sum the moments about the right side. And same thing we just did. Pn times h over 2 minus c sub c times a over 2 minus c sub s times d prime plus t times d, right? The two that are turning counterclockwise are positive. The two turning clockwise are negative. And I run the numbers. I get 4641 kip inches, or 386.8 kip feet. Since epsilon t is equal to epsilon y, which is 00207, 00207 is still less than 004. So therefore, phi is equal to 0.65. Phi Pn is 0.65 times Pn, which is 271. And phi Mn is 0.65 times Mn. 0.65 times 386.8 is 252 kip feet. So that's point C. Do I have any questions about point C?
Professor, the AG is the area A times the height?
Yes.
Okay.
Yeah.
And PN, can that sometimes not be directly in the center, like H over 2?
No. No.
Okay.
No. It is always, always, always in the plastic center.
Okay.
And this is, as you can see, this is a symmetrical column, so the plastic center is the center of the column. But that's how we are defining this. That's why at the very beginning I said a column with an axial load and a moment is equivalent to a column with an axial load at a certain eccentricity. We did that so that we can show that by equivalency that a column with an axial load right down the centroid with a moment is equivalent. So that's actually a great question. Pn is always at the plastic center of the column.
Okay, thank you.
Okay.
Professor,
Yes.
at what step did you calculate the centroid? I kind of missed that when you calculated the centroid.
This one I did not, because as by observation, it is symmetric.
Ah, okay. So yeah, it's not necessary because you already know where it is.
I already know where it is, yes. But if this was 4 number 6s and this was 4 number 11s, then it would not be
Yeah, that was
symmetric.
gonna be my second question. What if the steel was different at those? Okay, that's my second question.
Yep, if the steel was different, then it's not symmetric. You'd have to calculate the plastic centroid. If these D primes here were not the same, you would have to calculate. So anything that would throw this thing from being symmetrical, in this direction, would force you to calculate a plastic centroid. But I'm not going to do that to you. All the columns we're looking at are going to be symmetric.
Can we consider the coverage or the clear spacing to be 2.5 typically?
Yes.
Okay.
Yeah. Unless it's been defined as something else, as so is often the case. I forget to put that on there. So if I don't tell you anything, you can just assume 2.5. Okay, so next point, we got 2 points to go. The next point is defined as the strain in the steel is 0.05. So by definition, the tensile steel has yielded because 0.05 is greater than 0.0207. And from similar triangles, same as we did before, we can solve for little c, but this time, the concrete is always 0.03, but this time the steel is defined as 0.05. So since I know that, I can solve for little c. So little c is 13.5, 0.03 over 0.03 plus 0.05, again, just similar triangles, gives you 5.06 inches. So A is beta 1 times c. Guys, starting to see a pattern here? You kind of solve these. Most of these are very similar.
Yeah, so Professor, your condition will change, like your epsilon s will change depending upon the point that you're at, correct? So it's not always, the reason why you said that the epsilon s is 0.005 is because you said at point D that epsilon t is 0.005. Is that why?
Yes, but that we just chose that.
Oh, okay.
We chose that because what we're doing, just kind of back to the big picture, we're picking the minimum number of points to define the interaction curve. You could pick many, many more points. You could analyze it at epsilon t equal to 0.06, 0.05, 0.04, 0.03. You could go through this whole exercise 200 times and get a really, really accurate version of the interaction diagram. We're doing the minimum. Minimum is like 5 points.
Okay.
Okay?
Yeah.
So at 0.05, C is equal to 5.06, A is equal to 4.05. Notice A is getting smaller and smaller. So the compression in the concrete is 0.85 F prime C, AG minus AST. And again, you can see the pattern. We're doing the same thing. A now is 4.05 times 16 minus 4 is 258.4 kips. Epsilon prime S for the compression steel is, this is the same equation. I'm kind of skipping, or not skipping steps. I'm just not writing them fully out because I'm repeating what I did in the previous points. So epsilon prime S is 0.0152. Clearly hasn't yielded. So F prime S is 0.0152 times 29,000 KSI. You get 44.02 KSI. The force in the compression steel, 44.02 times 4 square inches, 176.1 kips. T is going to be yield times the area. You know it's yielded because we're at 0.05, and you get 240 kips. Sum the forces in the vertical, solve for Pn. And just like before, we have 258 plus 176 minus 240. Pn now is 194.5. Sum the moments about the right-hand side, and Pn times h over 2 minus c sub c times a over 2 minus c sub s, I think I did this in every slide, times d prime, plus t times d. Plug in all the values. You get 3832 kip inch, or 319.4 kip feet. Now, here's the interesting part about picking this point. Since epsilon sub t is greater than or equal to 0.05, phi is now equal to 0.9. So this applies to both Pn and Mn. Pn is 0.9 times Pn, or 175. Mn is 0.9 times Mn, 0.9 times 319.4 is 287 kip feet. So now this is point D. We have point D. Any questions about point D?
Professor, how did you find AS prime again? Can you explain how it's 4?
It is just the steel that is inside of A.
Okay.
So 4 number 9s is 4 square inches of steel inside of A. Remember, maybe this would help if anybody's getting a little lost. If I trace straight up, then A, this is your area in compression, right? This is a side view. This is a top view. So this is your area of compression. So 4.05 times 16 is this area minus 4 square inches is minus these 4 bars.
Oh, I see. Okay, thank you.
Okay. Okay, last point. Let's do zero axial load. So really this last point is analyzing this like a beam. Problem becomes a compression steel beam problem because you have steel in tension and steel in compression. So rho is 4 over 16 times 13.5 because D is 13.5, 0.1852. Rho prime is actually the same thing, 0.1852. So if rho minus rho prime is greater than all of this, then the compression steel will yield. And 0.1852 minus 0.1852 is equal to 0, so it's not. The steel does not yield. So we write our force equations in terms of little c, just like we did for compression steel. So the compression in the steel is A prime S times F prime S. And I write that in terms of little c. And I plug in D prime. And so this is my function for little c. If you plug in little c, you'll get the whole compression force. The tension is defined 4 times the yielding of the tension steel, 240 kips. And the compression in the concrete, 0.85 F prime C B times A, which is the same as 0.85 F prime C B beta 1 C. And I know everything in there except for C, so I get 54.4 kips per inch times C. Equate it all, tension minus compression steel minus compression in the concrete equals 0, and I get a quadratic. Solve the quadratic for 3.25 inches, and A is equal to 0.8 times 3.25, 0.26 inches. And F prime S is 87 C minus D prime over C. Plug in the values, 20.1 KSI. C sub S then is 4 times 20.1 is 80.3 kips. T is 240 kips. And C is 0.85, 5,000 PSI, 16 wide, and A was 2.6, goes there, 176.8 kips. Now I have all 3 components. I can sum my moments about the top of the beam. Tension steel, compression in concrete, and compression in the steel. I get 2809 kip inch, or 234.1 kip feet. Phi Mn is 0.9 times Mn, which is 211 kip feet. And by definition, the axial load is 0 kips. That was how we defined the problem. So that gives us our 5th point.
Professor?
Yes.
I guess conceptually, I'm just a little bit confused about why you analyze it exactly like a compression steel beam, considering it is a column. I don't know, just something about that confuses me, and I'm not quite sure why.
Well, it's not a column. A column is defined as a concrete member carrying axial load.
Ah,
This is a
okay.
concrete member carrying no axial load.
No axial load. Yeah.
So,
Okay, that makes sense.
so
Right.
now
Okay. The definition
it's,
of a column.
yeah, it's really just somebody took a beam and stood it on end.
Stood it
And
up. Yeah. Stood it
yeah,
up vertical. Okay.
exactly. Yes.
Okay.
Okay.
Thank you.
Okay. Well, here's where we pull it.
Sorry.
Yeah.
So how do we know that phi is 0.9? Is that given, or is there a way to determine that phi is 0.9?
Good question. Good question. I actually skipped it. You know it because epsilon sub t will be greater than 0.005.
Okay, so you had to do the same verification in order to determine that phi is 0.9, correct?
You do. I skipped it on this one because I know something special. What I know special is that point D was already at 0.005. So point E is going to be much larger than 0.005.
Okay, that makes a lot of sense.
Yeah, but you make a great point that to somebody who's looking at this for the very first time, that may not have been obvious. So I probably should have had an epsilon sub t equals check to show that epsilon sub t is greater than 0.005. But I know that it will be because C from point E is smaller than the C we got from point D, where we already had epsilon sub t exactly equal to 0.005. So I kind of I didn't even think about it. I just kind of ran it through my mind that I know as I progress down from point A to B to C to D to E, epsilon t is always getting bigger. But I didn't actually show that.
Because C is getting smaller.
Because C is
little
getting,
c is getting.
yeah, exactly. Yes, because C is getting smaller, epsilon t is getting bigger. Yep.
All right, thank you.
That actually makes really good sense.
Professor, can we, in a test to save time, skip that step too, but make a
No.
note that the previous point we know it's going to be larger? Or no, you want to see it?
I ain't gonna do that.
Can we put like something like by observation?
All right, fine.
Okay, perfect.
Okay, by observation, by astute observation. Okay, let's pull it all together though. I mean, these are great questions, but you're just like right about to fall over the cliff of great understanding. So let me get through the next few slides, and then we'll stop and make sure this sinks in. We have generated 5 points. It was a lot of work. What was the point of generating 5 points? Well, here it is. 1, 2, 3, 4, 5. 1, 2, 3, 4, and then this fifth one here was really 2 and 1. But we calculated phi p naught as 997, and that's just a continuation of this slope. And we calculated phi pn at 798. And remember, this is that minimum eccentricity deal. So you draw this straight across until you intercept this slope. Then we plotted, this was point B, point C, point D, and point E. And we just use, for simplicity, we just use straight line segments between all 5 of these points. So the dotted line is not actually part of your interaction diagram. This is not part of what is acceptable, but you kind of need this point up here to draw this slope, to intercept between these two correctly, because we didn't actually solve for that point. That point would be much harder to find. Okay, so does that make sense to everybody? This is your 5 points that we just calculated.
Yeah, that makes sense.
That makes sense to me too.
Yes, it does.
Perfect, great. So now we have created a diagram. Now notice the very beginning of the problem, I gave you PU is equal to something, MU is equal to something. We never used those numbers. Those two numbers never went into the creation of this interaction diagram. But here's where those numbers are going to come. So we've plotted A through E to create this diagram, and there are those two numbers. On the interaction diagram, we plot our design load demand, MU, PU. Since this point is inside the curve, the column design is adequate for this design. So you create the whole interaction diagram irrespective of the loading, and then you use it to check your loading, like so. Most designs in practice will have multiple load cases, all of which will be plotted and confirmed to fit inside the interaction diagram. By calculating and plotting more points, the diagram will become more and more accurate. This is like the bare minimum with 5 points. Let's see. More accurate. Oh, okay. And this is that dotted line, the point where the phi transitions from 0.65. So this is that balance point right there. And this is the point where phi equals 0.9. So you have this little bump in moment capacity because of this transition in phi from 0.65 to 0.9. And so kind of put like a little dolphin nose on there.
Professor?
Yeah.
Can points exist outside of the curve?
If you have a load out here,
Yes.
that means that the column would not be able to carry the load. It is beyond the strength of the column.
Okay.
So that's what it means. If the point is inside, it works. If the point is outside, we're not analyzing what the point actually does to the column. We just know that this is the boundary of all things working. Anything outside the boundary does not work.
Doesn't work.
Okay. And here's the minimum eccentricity. I am trying to get to, yeah. We're going to make it. We're going to make it. That's what I'm trying to get to. This was done by a software. So this is called SP column. And this is the exact column that we just analyzed ourselves. And this is what a professional diagram, which integrated over hundreds of points. This is what the real diagram looks like when it's analyzed over many, many points. But as you can see, it is pretty darn close to ours over just 5 points. So the computer software is available to calculate very accurate interaction diagrams. Okay, and I think this is about as far as we're going to get tonight. Any parting thoughts or last minute questions?
Professor, I wanted to ask a question going back to beam design. Is that okay?
Sure, you have exactly 60 seconds.
I was just confused when to design for the service load still or for the factored load, because I know earlier on we were finding MU with the factored load.
Yes.
But you said sometimes you prefer to find the service load.
No. It has nothing to do with preference. It is very, very defined. There's an absolute black and white, right or wrong answer. When you are checking the capacity of anything to do with concrete, capacity is always done with factored loads. So that could be flexural capacity, shear capacity, axial capacity, torsional capacity, anything based on capacity, which basically is saying at what point will it fail, you always check that with factored loads. The opposite of that, anything that you're checking that has to do with serviceability. Serviceability is cracking or crack widths or crack spacing or deflections or vibration analysis. Those are all done with service loads. If a beam cracks, it hasn't failed. If a beam deflects too far, it hasn't failed. See what the difference is? Failed means that it failed. It collapsed. That was its capacity. You exceeded it. Now it's on the ground. Serviceability issues are it hasn't collapsed, but it doesn't look very good. That's the defining difference between service loads and factor loads.
Okay, that helps a lot. Thank you.
You're welcome. Okay, everybody. Remember, I got office hours. If any of this was confusing and or I blew by it way too fast for you, please review the lecture notes and get into the office hour or email me if you can't make it at that time. We'll figure out another time. And other than that, we will see you. Everybody have a great weekend.
Thanks,
Bye,
Professor.
Professor. Have a great weekend.
You too. Okay, let me, Damien, are you still on the line? You are still on the line.
Yes.
Tomorrow actually is not good for me. I have to go out of town again, which is becoming more of a regular thing. It's a family thing. So tomorrow wouldn't work for me, but maybe Monday, certainly Tuesday.
First of all, I'm sorry to hear that about your family, but yeah, I think I'll just attend during regular office hours then.
That would be fine, but also if you have questions, normally during the office hour, I have maybe anywhere from 3 to 5 or 6 people at the same time, because everybody likes to hear what everybody else's questions are. If
Right.
that's okay, then great, join us then. If you want it to be more one-on-one, we could fix up something at some other time.
All right, I'll follow up with an email
Okay.
discussing what is the best available time. So either Monday or Tuesday would be preferable. So I'll just let you know, okay?
Okay, sounds good.
All right. Thank you, Professor. Have a nice one.
You too. Thank you.